Today in the Physics Funhouse, we're discussing electric circuits. Typically, when we think of electric circuits, we think of things like batteries and flashlights and light bulbs and all those fun sorts of things. And that's kind of where we're going to start today, just the very basics of an electric circuit. So in order to have an electric circuit, we need to have two things. Number one, we need to have a source of electric potential to provide energy to charges. So a battery would be a good example of that. And your standard D-cell battery has a voltage, it's stamped on there somewhere, of 1.5 volts. Actually, all of these cylinder batteries, like AA's, AAA's, and C's and D's, all have the same voltage. This guy just has more charge, so it has more energy. It'll last longer in a given application. So I've got one here just kind of clipped into a little battery holder like that. And then the second thing we need is some sort of conductor. And typically when we think of conductors, we think of wires. So these wires are just designed to like slip over those little posts on this little circuit board thing here. But any metal would be a conductor, and so I can use a paper clip to conduct an electric current as well. And there's also some non-metals that are conductors, graphite being a good example. I'm not going to connect just a wire by itself to a battery because the energy that the battery gives charges in my circuit has to be lost as thermal energy somewhere somehow. And if I just connect a single wire there, we would call that a short circuit, that energy is going to be dissipated very quickly and very rapidly, resulting in my battery getting hot. In fact, so hot that the battery itself could explode and like spray battery acid and nasty chemicals everywhere. So rather than just connect a wire and blow a battery up, that's not cool, I'm just going to connect a light bulb to it. So here's just a standard light bulb we use in physics labs. It's not going to be very bright, but when I connect it and go, let there be light, the light bulb glows. If we pause a few seconds and run across the room and turn the lights off, we should be able to see it glow better. So with the lights in the classroom turned off, we should be able to see that my light bulb glows very well. If I disconnect one of these wires, the light bulb goes out. So the first rule of circuits is that we need a complete conductive path from one end of the battery all the way around to the other. If I break it on either side of the light bulb, I no longer have an electric circuit, and the light bulb turns off. So what's happening inside the wires, our very simple model, is that charges are moving from the positive end of the battery through the wires. When they get to the light bulb, they lose energy, and that energy is lost to thermal energy. You see the light bulb glow. And then the charges with much less energy make their way around to the other end of the battery where they join on the negative charges. And one thing we're going to do a little bit later on is kind of look at what the inside of a battery looks like. So there's our very first electric circuit. Let's draw a circuit diagram illustrating this. And for that, I might want to turn the lights back on. In our circuit diagram, we're going to use symbols to represent things like batteries and light bulbs. The symbol that we're going to use for a battery is two parallel lines, one longer than the other. And the longer one represents the positive end of a battery, and the shorter one represents the negative end. So the banded side of the battery is the positive end, the other side is the negative end. So my battery is aligned like this. For all the things we do in Physics 1, and most of the things that we do in Physics 2, the polarity, or which way the battery is oriented, doesn't matter. So if I take this battery holder and I take the battery out, and then I switch it around, the light bulb still lights up with the exact same brightness and everything else that it did before. So most of the time, it's not going to matter how we draw our battery. If we draw our battery with the two sides being the same length, that's not a battery. That is a capacitor. Worth knowing, especially in Physics 2, but for right now, we're not going to worry about capacitors. I mentioned that to make sure you know why you need to draw one side longer than the other. The light bulb, we could draw like this. Kind of like a circle with a filament inside of it. You'll see that symbology used, but what I prefer you to do is draw a light bulb as a resistor. And a resistor is a somewhat of a squiggly line, kind of sort of like that. And so you can draw a light bulb like that, but if you do, it's not going to be clear to you that a light bulb is a resistor. We'll talk more about what that means in a little bit. And you're also going to confuse the symbol for a light bulb with the symbol for a meter, like an ammeter or a voltmeter. So our first circuit diagram here would just look like a battery connected to a resistor, just like that. So that diagram there matches this circuit here. Actually doesn't match it exactly because I turned my battery around backwards. So if I wanted to indicate that, I could. Just make that side bigger. By the way, we just draw straight lines for wires. And when we draw circuit diagrams, we draw them perpendicular to each other, the wires perpendicular to each other. And we try to avoid having the wires cross one another. There's no situations, I believe, in Physics 1 or Physics 2 where we have to have wires crossing each other. Just something we try to avoid drawing for clarity's sake. Because if we do have wires crossing each other, then it can look like a junction, something we're going to learn about in just a few minutes. All right, so there's our very, very first circuit diagram. So the next question might be, well, how can I control how bright that light bulb is? If I replace this light bulb with a different light bulb, so notice this one's a little bit smaller. That light bulb is glowing. It's just not glowing very brightly. It's almost impossible to see. And so by changing the properties of the light bulb, I change the current through it. And the specific property that I'm changing is called the resistance, which we'll be learning about in a little bit. But that's simply the resistance to the flow of charge, like how good a conductor it is. So this light bulb is not as good a conductor as this light bulb. But since we're videoing this, let's stick with the brighter of the two. The second way that I can change the brightness of my light bulb, change the amount of current flowing through my circuit, would be to add more energy to my charge. So to do that, I would just need more batteries. So let's disconnect this, kind of set that dude like that, grab another battery holder. So it is important if I add several batteries together that I line them up so that the positive end of one is in contact with the negative end of the other, just like you would put batteries in a flashlight. So now when I connect the second battery in there, now that my battery holder is working, you should notice that the light bulb is much brighter than it was before. So with the lights off, we can see that our light bulb is much brighter than it was before. I can kind of sort of bypass this extra battery. Just going to take this wire off and move it over here. So that's a circuit with one battery. There's a circuit with two batteries. So you can notice how much brighter the light bulb is with the additional electric potential, aka voltage, pushing the charges through the circuit.